Welcome to the Unseen Shelf. Today, we step beyond the body, beyond the organism itself, to explore a revolutionary idea, one that challenges how we perceive life, evolution, and the reach of our very own genes. In The Selfish Gene, Richard Dawkins argued that genes are the true units of selection, the hidden architects of survival. But what if their influence extends far beyond the bodies they build? What if evolution isn't just about flesh and bone, but also the ripples our genes send into the world around us? This is the extended phenotype, a bold expansion of evolutionary thought. From the intricate webs of spiders to the towering dams of beavers, from the unseen manipulations of parasites to the very way organisms shape their environment, Dawkins takes us on a journey that reshapes our understanding of natural selection itself. What if genes don't just control the creatures they inhabit, but the world they touch? What if survival isn't only about the fittest organism, but the most effective gene influence? This is the hidden story of evolution, one where the reach of life stretches far beyond the skin it wears. Join us as we uncover the unseen logic of nature, the silent architects of adaptation, and the extraordinary ways life bends the world to its will. This is the extended phenotype, and this is the unseen shelf. Part 1 introduces foundations of the extended phenotype. Dawkins lays the foundation for his argument, explaining the limitations of traditional views of evolution and introducing the idea that genes can extend their influence beyond the organism. Let's explore Chapter 1, Necker Cubes and Buffaloes. The Necker cube shifts as you look at it. A flicker, a subtle change, and suddenly the front face becomes the back, then shifts again. Neither perspective is more real than the other, only different depending on where you focus. Evolution is much the same. For centuries, biologists have viewed it through the lens of organisms, living beings struggling, adapting, and surviving. But what if the real battle is not between creatures, but within them? What if the fundamental unit of evolution is not the organism, but something smaller, something unseen? On the African plains, a buffalo moves slowly across the grasslands, its thick hide home to tiny parasites, ticks that burrow into its skin, feeding on its blood. At first glance, the buffalo seems to be the dominant figure, a towering creature navigating its world. But the tick, too, is a survivor, following an instinct that has been shaped by countless generations of natural selection. And if the buffalo is merely acting out the program encoded in its genes, is the tick not doing the same? Even the birds that hop onto the buffalo's back, plucking ticks from its fur, are they participating in the buffalo's survival, or simply acting out their own genetic imperatives? For years, we have understood evolution as the survival of the fittest organism, the lion with the strongest muscles, the eagle with the sharpest vision. But a shift in focus reveals something different. Natural selection does not act on whole creatures, but on the genes that construct them. The lion does not fight to survive. Its genes do. The eagle does not sharpen its vision for its own sake, but because the genes that shape it succeed through that clarity. Organisms, from the towering buffalo to the smallest tick, are merely vessels, vehicles carrying genes forward in time. The Necker cube flickers again, revealing another truth. Genes do not stop at the edge of the body. Their influence stretches outward, shaping the world beyond skin and bone. A beaver's dam is not just a structure. It is an extension of its gene's survival strategy. A spider's web, a parasite's control over its host, the social instincts of ants, each a thread in the web of life, each an unseen force driven by the silent architects of existence. And so the way we see evolution must change. The buffalo, the tick, the bird, the beaver, the spider, they are not the central players, only reflections of something deeper. The true force shaping life is hidden beneath the surface, influencing not just bodies but entire ecosystems. This is where the journey begins, where we step beyond the organism and into the realm of genes. The world we see is only part of the story. The real battle is unseen. Chapter 2, Genetic Determinism and Gene Selectionism describes how genes influence traits and behaviors, not through rigid control but by shaping tendencies and probabilities, with natural selection acting at the gene level rather than the organism. For centuries, people have debated the role of genes in shaping life. Some have feared that too much emphasis on genetics leads to fatalism, that if our instincts, behaviors, and abilities are dictated by our DNA, then free will is an illusion. Others have argued that organisms are more than their genes, that the environment, learning, and experience play an equally vital role. But this debate, Dawkins argues, is often based on a misunderstanding. The power of genes is not absolute control, but influence, shaping tendencies and probabilities rather than rigid outcomes. A child raised in a multilingual household may grow up speaking several languages, while another, raised in isolation, may struggle with basic speech. Their environments differ, but the biological machinery allowing for language, complex neural pathways shaped over millions of years, remains the same. Genes do not dictate whether the child will speak French or Mandarin, but they do make it possible. Genes set the stage, the environment writes the script. Natural selection, then, does not act on whole organisms, nor even on entire species. It works at the level of genes, selecting for traits that improve survival and reproduction. But genes do not operate in isolation. They interact with one another, competing and cooperating within the same body. A gene that increases strength might be beneficial, but only if it does not also demand too much energy. A gene that sharpens eyesight may provide an advantage, but only if it does not weaken other senses. Every trait is a compromise, an evolutionary balance between costs and benefits, shaped over generations by the pressures of survival. And so, the fox moves forward, its path determined not by conscious reasoning but by instincts fine-tuned over millennia. Its ancestors, those who survived, carried the genes that allowed them to be fast enough, cautious enough, resourceful enough. And now, in this moment, those same genetic instructions guide the fox through the darkness, ensuring that its lineage, its genes, may yet live on. Chapter 3 Constraints on Perfection explains that evolution does not produce perfect organisms, but instead works with constraints, trade-offs, and historical limitations, favoring traits that are good enough for survival rather than optimal. It is easy to assume that evolution strives for perfection, that over time, creatures become ever stronger, faster, smarter. But nature does not optimize for an ideal form. It simply favors whatever works well enough to survive and reproduce. Genes, too, are constrained. An organism's DNA is not a blank canvas where new traits are designed from scratch. It is an ancient manuscript, rewritten and edited over countless generations. Each mutation, each adaptation, builds upon what came before, limited by the materials at hand. Even when a trait provides an advantage, it cannot evolve in isolation. A stronger jaw may mean a heavier skull, requiring sturdier muscles, which in turn demand more energy. An animal cannot evolve infinite strength, infinite speed, or infinite intelligence, because every gain must be balanced against cost. Natural selection does not favor perfection. It favors survival. Evolution is not an architect crafting the best possible form. It is a tinkerer, making do with what is available, shaping life not toward perfection, but toward what works for now. Chapter 4 Arms Races and Manipulation explores evolutionary arms races, where species continuously adapt in response to each other, such as predators and prey or parasites and hosts, while also examining how manipulation, like parasites altering host behavior, shapes survival strategies. The gazelle senses the danger before it sees it, a ripple in the tall grass, the faintest shift in the wind. Instinct takes over, muscles coil, and in a blur of motion, it leaps away just as the cheetah explodes into pursuit. This is a race older than time itself, a battle fought not just between predator and prey, but between the genes that shape them. The cheetah runs faster, because those before it ran fast enough to catch their quarry. The gazelle leaps higher, turns sharper, because those before it escaped. Each generation, the stakes rise, the adaptations sharpen, yet neither gains a final victory. This is the arms race of evolution, a relentless cycle where survival demands constant improvement. But not all battles are fought with speed and strength. Some are waged in the mind, in the unseen tug of control that one creature exerts over another. A parasitic worm burrows into the body of an ant, rewriting its instincts, forcing it to climb to the top of a grass blade at dusk. The ant does not know why, only that something compels it to stay there, motionless, waiting. A grazing animal passes by, bites into the grass, swallows the ant, and the parasite's journey is complete. It has reached its true host. This is not a conscious strategy. It is not the parasite itself that chooses to manipulate its host. Rather, over countless generations, the genes of parasites that successfully influenced their host's behavior survived, while those that did not perished. Nature is filled with such hidden battles. A wasp injects its eggs into a caterpillar, its larvae growing inside, consuming their host slowly, keeping it alive just long enough. A virus alters the aggression of an infected animal, making it more likely to bite and spread the infection. Even in humans, some pathogens may influence behavior in ways still not fully understood. The genes of these manipulators persist because they succeed in a game older than any single species, the game of survival. The gazelle, the cheetah, the parasite, the host. Each plays its part, each adapts, each is shaped by the pressures of natural selection. Yet there is no final winner. The race continues, the arms build, the strategies evolve. The only constant is the struggle, written into the very code of life itself. Now we're getting into part two, which explores how genes extend their influence beyond the individual organism, shaping behaviors, interactions, and environments through mechanisms like manipulation, cooperation, and external structures, redefining the scope of natural selection. The first chapter of part two, the active germline replicator, introduces the core concept of the extended phenotype, arguing that a gene's influence extends beyond the body of the organism, shaping behaviors, structures, and even the environment to enhance its own survival and replication. The beaver works tirelessly, gnawing at the base of a tree, its teeth carving through the bark with practiced efficiency. The trunk groans, tilts, and then crashes into the water, sending ripples across the pond. The beaver does not stop. It gathers branches, mud, and stones, layering them with precision, reshaping the flow of the river, crafting a dam that will protect it home, slow the water, and create a deep pool where it can survive the harsh winter. This is instinct, a behavior passed down through generations. But what if it is more than that? What if this dam is not just a structure built by the beaver, but an extension of the genes that created it? For centuries, biologists have viewed evolution as a process confined to the body. A lion's sharp claws, a hawk's keen eyesight, a cheetah's speed, all understood as traits shaped by natural selection, locked within the organism itself. But genes do not stop at the boundary of skin and bone. Their influence extends outward, shaping the world beyond the body, bending the environment in ways that increase their survival. The beaver's dam, the spider's web, the bird's nest. Each of these is not simply a tool, but a genetic expression, an external product of natural selection. Even behavior itself falls under this unseen influence. A parasite that manipulates its host into suicidal actions is not acting with intent, but rather as a vessel for genes that have, over time, succeeded in altering another species. A cuckoo lays its eggs in another bird's nest, tricking its unwitting host into feeding and raising a chick that is not its own. This is not mere chance. The genes that shaped the cuckoo's deception persisted because they worked. And so behaviors, just like physical traits, are shaped, refined, and extended beyond the organism, leaving an imprint on the world itself. The beaver does not know that it is altering the ecosystem, nor does the spider understand the geometric precision of its web. But their genes do, at least in the silent language of evolution. The dam, the web, the manipulated host, these are not separate from the beaver, the spider, or the parasite. They are part of the same continuous thread, the extended reach of genes beyond the body, stretching into the environment, shaping the world in ways unseen yet undeniable. Organisms, groups, and memes. Chapter 6 explores how parasites manipulate their host's behavior as an example of the extended phenotype, demonstrating that a gene's influence can extend beyond its own organism to control another for its own survival. The ant climbs higher, gripping the slender blade of grass as the sun begins to set. It should be searching for food, returning to its colony, following the invisible trails of scent laid down by its kin. But it does none of these things. Instead, it remains frozen in place, mandibles locked around the grass, waiting. It does not know why. It does not know that deep inside its body, something else is in control. A parasite, a silent puppeteer, has taken over, rewriting the ant's instincts to serve a purpose not its own. This is not an accident. The parasite, Dicrocelium dendriticum, must reach the stomach of a grazing animal to complete its life cycle. The ant is simply a vessel, a temporary means of transport. Over countless generations, the genes of parasites that successfully altered their host's behavior survived, while those that failed disappeared. There was no conscious intent, only the relentless refinement of nature, selecting for manipulation that worked. And so the infected ant climbs, night after night, waiting to be swallowed by a passing cow or sheep, ensuring that the parasite's journey continues. Manipulation of hosts is not rare. It is woven into the fabric of life. A wasp injects its venom into a cockroach's brain, dulling its escape response, turning it into a passive vessel for the wasp's eggs. A rabies virus travels to the brain of its host, increasing aggression, compelling it to bite, spreading the virus to a new victim. Even Toxoplasma gondii, a parasite found in rodents, alters their fear response, making them attracted to the scent of cat urine. The infected rat does not flee. It approaches, and it dies, but the parasite survives, reaching the gut of the cat, where it can reproduce. Dawkins argues that this is more than just biological warfare. It is an example of the extended phenotype, proof that genes can exert influence beyond their own bodies. The parasite's genes shape the behavior of an entirely different species, bending it to their will. The host is not the true agent of its actions. The genes of another have taken control. And so the ant remains where it is, clinging to the grass, as a cow grazes nearby. It does not know that it has been rewritten, its actions no longer its own. But its genes do not matter anymore. Only the genes of the parasite, the unseen master pulling the strings, have ensured their survival. The ant is lost, but the parasite has won. Third chapter of Part 2. Chapter 7 explores the conflict between outlaw genes that act selfishly to their own advantage and modifier genes that evolve to suppress or regulate them, highlighting the genetic struggles within organisms. Deep within the strands of DNA, a quiet battle rages. It is not the struggle of predator and prey, nor the contest of species locked in an evolutionary arms race. This war is different. It is fought within the body itself, between genes that should be working together but sometimes rebel. Some genes follow the rules, ensuring the organism functions as a coordinated whole. Others do not. These are the outlaws, rogue genes that manipulate the system for their own advantage, often at the expense of the very organism that carries them. Natural selection favors genes that increase survival and reproduction, but it does not demand cooperation. If a gene can find a way to promote its own spread, even if it harms the organism in the process, it may still succeed. Some of these outlaws hijack reproductive systems, ensuring their own replication while reducing the fitness of their host. Others distort inheritance itself, forcing their way into the next generation at the cost of genetic balance. Take the case of meiotic drive, a phenomenon where certain genes manipulate the process of reproduction to favor their own transmission. Instead of following the usual 50-50 inheritance pattern, these selfish genes ensure they are passed on more frequently, even if they weaken the organism. Some male mice carry distorter genes that sabotage sperm-carrying rival versions of the genome, ensuring only their preferred genes survive. The result? Fewer viable sperm, reduced fertility, and a conflict that weakens the very body these genes depend on. But evolution does not allow unchecked chaos. Over time, other genes, modifiers, evolve to suppress these outlaws, restoring balance. These genes do not act for the sake of the organism. They simply survive because they counteract the destructive effects of selfish mutations. A constant struggle unfolds, rogue genes finding new ways to cheat the system, while modifiers evolve to keep them in check. And so, inside every living thing, this hidden conflict continues. The body appears unified, a single entity with one goal: survival. But beneath the surface, the genes wage war, a delicate balance between cooperation and betrayal. The organism is not a harmonious machine. It is a battleground. Outlaws and Modifiers. Chapter 8 explores the concept of selfish DNA and jumping genes, genetic elements that replicate themselves within the genome without benefiting the organism, challenging traditional views of natural selection and raising questions about the nature of genetic evolution. Deep within the genetic code, beyond the genes that shape eyes, muscles, and instincts, there are fragments of DNA that seem to serve no purpose. They do not build proteins, do not contribute to survival in any obvious way. Yet, they persist, copied and carried forward through generations. These are the selfish elements of the genome, genes that exist only to replicate themselves, passengers in the great machinery of life. For decades, biologists assumed that every part of DNA must have a function, that natural selection would purge anything unnecessary. But scattered across the genome are sequences that do nothing but copy themselves, jumping genes, transposons, and selfish DNA elements that propagate without concern for the organism they inhabit. Some of these sequences are harmless stowaways, while others disrupt vital genes, causing mutations and disease. Yet they survive because evolution does not design for perfection. It only favors what persists. Barbara McClintock first discovered these rogue genetic elements in maize, observing how certain genes could move from one location to another, altering the plant's traits. These jumping genes were later found in nearly all living organisms, from bacteria to humans. Some transposons copy themselves and insert randomly into the genome, like parasites within the very fabric of life. Others leave traces of their past, broken and silenced by mutations, remnants of ancient invasions. Dawkins challenges the idea that natural selection always works for the good of the organism. The genome is not a perfectly curated blueprint, but a battleground of competing interests. Some genes act in harmony, working together to build a functioning body. Others exploit the system, replicating at the expense of stability. Evolution, blind and indifferent, allows both to exist, selecting not for efficiency, but for endurance. Even within our own DNA, these silent passengers remain. Some have been repurposed by evolution for new functions, while others linger as genetic fossils, echoes of ancient struggles. They remind us that life is not always shaped by purpose, but by the relentless persistence of whatever manages to survive. The last chapter of Part 2, Selfish DNA, Jumping Genes, and a Lamarckian Scare critiques the adaptationist perspective, arguing that not every trait is a direct result of natural selection, and some features may arise as byproducts, constraints, or neutral evolutionary changes rather than adaptive advantages. The polar bear's fur is white, blending seamlessly into the Arctic snow. It is easy to see this as a perfect adaptation, natural selection sculpting the ideal camouflage for survival. But nature is not always so intentional. Not every trait exists because it was finely tuned for a purpose. Some are mere byproducts, accidental consequences of other evolutionary changes. The world is filled with traits that exist not because they were designed to, but because evolution is not a perfect engineer. It is a tinkerer working with whatever happens to arise. For years, adaptationists have sought explanations for every trait, assuming that if something exists in nature, it must serve a function. Why does a zebra have stripes? To confuse predators, some say. Why do humans dream? Perhaps to process information. But Dawkins warns against seeing design where there may be none. Some features emerge not as adaptations, but as side effects of other changes, genetic drift, developmental constraints, or even historical accidents that never got in the way of survival. Consider the human chin. Unlike the beaver's teeth or the cheetah's speed, it serves no clear adaptive function. It does not aid in chewing or speech, yet it persists. It may simply be a byproduct of jaw structure, an evolutionary accident with no survival advantage. Similarly, some fish have vestigial eyes, remnants of ancestors who once relied on sight but now live in total darkness. These traits are not designed for their current environment. They are echoes of evolutionary history, carried forward because they do not hinder survival enough to be eliminated. Even within genetics, not all mutations are sculpted by natural selection. Some genetic variations spread through populations purely by chance, their presence neither helping nor harming the organism. A trait may persist not because it is useful, but simply because nothing has removed it. The assumption that every detail in nature must have a purpose is a dangerous one, leading to explanations that are more storytelling than science. The polar bear's white fur may indeed help it blend into the snow, but not every feature in nature has such a clear explanation. Some things exist not because they were perfected by selection, but because evolution works with what is available, not what is ideal. The world is full of traits that arose not by design, but by accident, and that, too, is part of the story of life. We are here at Part 3, which is the last journey of the book. Part 2 provided the evidence by establishing the core idea of the extended phenotype, demonstrating how genes exert influence beyond the individual organism. And Part 3 examines the broader implications of the extended phenotype, exploring how genes shape not only individual organisms but also behaviors, environments, and evolutionary history, while addressing the boundaries and limits of genetic influence. The first chapter of Part 3, An Agony in 5 Fits, examines 5 biological puzzles through different evolutionary perspectives, demonstrating how the extended phenotype concept helps explain complex traits, conflicts, and adaptations beyond traditional gene-centered views. A salmon swims against the current, its body straining as it pushes upstream. It has no choice. Something deep within it compels this journey, a force older than memory, older than the species itself. It will reach its spawning grounds, lay its eggs, and die. The cycle continues, unbroken for generations. But why? What invisible hand dictates such sacrifices, such instinctive obedience to a path set long before birth? Dawkins presents 5 evolutionary puzzles, biological enigmas that challenge simple explanations. Why do some organisms give their lives for reproduction, like the salmon? Why do certain parasites kill their hosts, while others coexist? Why do social insects sacrifice their reproductive potential for the good of the colony? These questions do not have a single answer, nor can they always be explained by traditional survival of the fittest reasoning. They require a shift in perspective, a view that extends beyond the individual and into the genetic strategies that shape life itself. Consider the kamikaze reproduction of the salmon. The energy it expends on its final journey ensures that its offspring have the best possible chance of survival. The salmon does not choose this fate. It is the result of genes that have been selected precisely because they promote reproductive success, even at the cost of the individual. The genes themselves do not die. They pass forward, carried by the next generation, their strategy proven effective once more. Or take the paradox of parasitic behavior. Some parasites, like certain tapeworms, live harmoniously inside their hosts, extracting nutrients without causing fatal harm. Others, like the rabies virus, drive their hosts to aggression and death, ensuring their own spread at the cost of the organism they inhabit. Why this difference? The answer lies in the parasite's method of transmission. If a parasite needs its host to survive long enough to spread, it will evolve restraint. If spreading depends on host death, as with rabies forcing its victim to bite, destruction becomes part of its strategy. Evolution does not favor kindness or cruelty, only what works. Then there is the puzzle of altruism among social insects. Worker ants toil tirelessly, never reproducing, dedicating their lives to the colony's queen. At first glance, this seems to contradict natural selection. Why would an individual sacrifice its own reproductive success for another? But the answer lies in relatedness. By supporting the queen, the workers ensure that their shared genes persist. The individual's survival does not matter, only the survival of the genetic code it carries. Each of these puzzles, different as they may seem, share a common thread. They are not shaped by the needs of the individual, but by the silent logic of genes. The salmon's sacrifice, the parasite's manipulation, the ant's selflessness. Each is a strategy honed by evolution, a reflection of genetic influence reaching beyond the body, beyond instinct, beyond even survival itself. The organism is not the final player in evolution. It is merely a vessel, a carrier of instructions written in DNA, instructions that shape not just bodies, but behaviors, interactions, and even entire ecosystems. The Genetic Book of the Dead. Chapter 11 introduces the concept of the genetic book of the dead, arguing that an organism's genes contain a historical record of past environmental pressures, reflecting the selective forces that shaped its ancestors. The lion moves through the tall grass, silent, unseen. Its muscles ripple beneath its golden coat, a body built for the hunt. Every inch of it, its claws, its powerful legs, the sharp focus of its amber eyes, tells a story written long before it was born. The lion does not know this. It does not know that its very existence is the result of an unbroken chain of ancestors, each shaped by the struggles of their time, each a survivor of selective forces that have long since faded. But its genes remember. Dawkins describes this hidden record as the genetic book of the dead, a biological archive written not in words, but in the silent language of DNA. Every living organism is a reflection of the past, shaped by the conditions its ancestors endured. The polar bear's thick fur, the giraffe's long neck, the hawk's razor-sharp vision. None of these traits appeared at random. They were sculpted by survival, the lingering echoes of ancient challenges. To understand this idea, imagine a landscape that no longer exists. A vast grassland stretches beneath a scorching sun, where swift predators and wary prey engage in an arms race of speed and endurance. We may never see this world, never know its full story, but we can infer its existence by studying the creatures that emerge from it. The genes that persist today are those that helped their ancestors thrive in conditions we can only reconstruct. The modern cheetah carries the imprint of past hunts, just as the Arctic fox bears the memory of frozen tundras that shaped its fur. But this book is not a perfect record. It does not preserve every detail, nor does it tell us of species that vanished, their genetic legacies erased. Evolution only records what worked, the solutions that proved successful enough to be passed forward. Some traits may now be obsolete, remnants of pressures that no longer exist. The flightless cormorant, trapped on its island, still carries the skeletal remains of wings once meant for the sky. The human appendix, a vestige of a dietary past, lingers as a quiet reminder of a different way of life. And so, the lion moves, a living testament to battles long won and lost. It does not know the world that shaped it, but it does not have to. Its genes are the product of that world, a whispered history passed down in the form of muscle, claw, and instinct. Life does not remember the dead, but DNA does. In every creature, the past endures, written in the only language nature has ever known. Host phenotypes of parasite genes. Chapter 12 explores how parasites manipulate their host's phenotypes as a striking example of the extended phenotype, demonstrating that genes can exert control beyond their own bodies by altering another organism's behavior for their own survival. Dawkins calls this a prime example of the extended phenotype, genes reaching beyond their own organism to shape another for their benefit. Leucochloridium paradoxum, the parasitic flatworm inside the snail, does not simply live within its host. It hijacks it, altering its behavior in ways that increase the parasite's chances of survival. This kind of manipulation is not rare. A wasp injects its venom into a cockroach, paralyzing only the parts of its brain that control escape reflexes. The rabies virus, too, alters behavior, making infected animals aggressive, increasing their likelihood of biting, spreading the virus to a new host. These parasites do not think or plan their strategies. Their success is the result of millions of generations of natural selection favoring genes that manipulate hosts in just the right way. In each case, the organism being manipulated is no longer acting in its own interest. Another creature's genes have taken control. And so, the snail continues its march into the light, its body no longer its own. The bird watches from above, hunger stirring. The parasite waits. Its success is not measured by its strength or intelligence, but by how well it can bend another to its will. Action at a distance. Chapter 13 refines the concept of the extended phenotype, arguing that while genes can influence environments and other organisms, there are limits to their reach, preventing an overly broad interpretation of genetic control. The beaver's dam stands firm against the river's current, a structure that alters the landscape, flooding valleys and creating deep pools where none existed before. It is a testament to the beaver's instincts, but more than that, it is an extension of its genes, an expression of survival beyond the body. Yet, as Dawkins concludes his argument, he draws an important boundary. While genes can shape behaviors, manipulate hosts, and alter environments, they do not control everything. The reach of the extended phenotype is powerful, but it is not limitless. Throughout the book, Dawkins has argued that natural selection does not just shape bodies. It sculpts actions, structures, and even the influence one species has over another. The cuckoo's trickery, the parasite's control over its host, the intricate web of a spider, all these are expressions of genetic influence that extend beyond the organism itself. But does that mean everything in the world is the product of genes acting at a distance? Can we stretch this idea to explain human culture, technology, or even social systems as genetic expressions? Here, Dawkins urges restraint. The extended phenotype is not a free license to explain everything through genetics. It is not meant to be applied so broadly that it loses meaning. While genes may influence how beavers build dams, they do not directly dictate the structure of human cities. While parasites can control a host's behavior, genes do not intend to shape entire ecosystems. The extended phenotype remains a biological concept, one that explains real evolutionary forces, but it should not be mistaken for a universal theory of influence. Just as evolution works within constraints, shaped by what is possible, not what is ideal, so too does the reach of genes. They can shape an organism's body, its instincts, and sometimes even the behaviors of others. But they do not control the world itself. They do not write history, nor do they dictate the course of civilizations. Natural selection may explain why beavers build dams, but it does not explain why humans build skyscrapers. And so Dawkins leaves us with a refined view of evolution. The extended phenotype is a powerful concept, revealing the hidden ways genes shape life. But like all scientific ideas, it has limits. Evolution is a force of nature, but it is not all-encompassing. Genes reach far, but not infinitely. Life is more than just survival. It is also shaped by chance, by environment, and by forces beyond the reach of DNA. The beaver's dam is a triumph of evolution, but it is still just a dam, not a destiny. The replicator as the prime mover. The last chapter of the book concludes the extended phenotype by reaffirming that the replicator, the gene, is the fundamental unit of selection, emphasizing that evolution is best understood from a gene-centered perspective while recognizing the limits of genetic influence. The river flows, carving its way through the land, indifferent to the stones it carries, the branches it moves, the lives it touches. Evolution, too, moves forward in this way, not with intent, not with purpose, but with a relentless, impersonal force of survival. The organisms that live within it, beavers building dams, birds weaving nests, parasites bending hosts to their will, are not the architects of this process. They are only its vessels, shaped by forces they cannot see. Their destinies written by something far smaller, far older, the gene. Dawkins closes his argument with a return to the fundamental truth at the heart of his work. The gene is the true unit of selection. It is not species that evolve, nor even individual organisms. These are temporary, fleeting arrangements, built and discarded over the vast span of evolutionary time. But the gene, the replicator, persists. Every beaver, every bird, every parasite exists because the genes that built them succeeded in being passed on. Evolution does not favor organisms. It favors the survival of genetic instructions, the silent code that ensures its own replication. Through the lens of the extended phenotype, we see how genes reach beyond the body, shaping not just the creatures they build, but also the worlds they inhabit. A spider's web is more than a tool. It is a structure shaped by genes, as much a part of the spider's survival as its fangs or its venom. A parasite's control over its host is more than an attack. It is an expression of genetic success. Genes do not simply sit within an organism. They ripple outward, influencing the environment, shaping behaviors, leaving an imprint on the world. But even as Dawkins champions this gene-centered view of evolution, he draws an important boundary. Genes are not omnipotent. They do not dictate history, control the rise and fall of civilizations, or determine the course of human culture. Evolution is powerful, but it is not a grand designer. It is a blind, unguided process that favors survival and survival alone. The extended phenotype reveals the unseen influence of genes, but it does not grant them limitless control. And so, the river continues its course, indifferent, unstoppable. The beaver builds, the spider spins, the parasite waits. But beneath it all, the genes endure, replicating, surviving, shaping life in ways both seen and unseen. The organism is only a temporary expression, a fleeting form. But the gene, the true player in the game of evolution, remains. Life is a vast and intricate web, woven not just by the creatures that walk, swim, and fly, but by the silent architects within them, the genes that persist beyond the rise and fall of individuals, beyond the fleeting forms of species. The organism, no matter how powerful, is a temporary vessel. The gene is the true survivor, the unseen force driving evolution forward, shaping not only the bodies of the living, but the very world they inhabit. Dawkins has taken us beyond the traditional view of natural selection, beyond the survival of the fittest creature, to a deeper truth. Genes do not merely build organisms. They extend their reach far beyond, influencing behavior, environment, and even the fates of other species. The beaver's dam, the spider's web, the parasite's manipulation of its host, these are not just biological quirks, but profound examples of how evolution works at the level of genetic influence. The extended phenotype is not a metaphor. It is a reality, a shift in perspective that reveals the true scale of genetic power. Yet, even as we acknowledge the reach of genes, we must also recognize their limits. Not every structure, not every behavior, not every phenomenon in the world can be traced back to the will of DNA. Genes may shape the instincts of beavers, but they do not dictate the architecture of human cities. They may influence behavior, but they do not govern the complexities of human culture. The extended phenotype is a powerful idea, but like all scientific theories, it is strongest when applied with precision. And so we end where we began, with a shift in perspective. To understand life is to see beyond the visible, beyond the individual, to the forces that shape existence itself. Evolution does not favor strength, nor intelligence, nor complexity. It favors survival. And survival belongs not to the creature, but to the code it carries. The river flows, the genes persist, and life, in all its unseen intricacy, continues. Thank you for your time and thoughtful engagement. If you have any reflections, insights, or topics you'd like to explore further, we'd love to hear from you. We look forward to seeing you again for our next book discussion. If you enjoyed this content, your support through a subscription and a like is truly appreciated. We will see you soon with the next book.